Okay, good morning, everyone. So it's my pleasure to introduce today's origin speaker, Aditya Arabhavi. Aditya completed his bachelor degree in mechanical engineering in Mysore, India. Okay, and then his master in aerospace engineering in the Netherlands at Delft. And since 2021, is a graduate student at the University of Groningen in the Netherlands, where he's working on JWST spectroscopy of planet-forming disks as part of the GTO, MIRI GTO team in Europe. So today is going to tell us what we are learning, especially this around very low mass stars. So take it away.
Thank you. So thank you for providing the opportunity to present, first of all, in the origins talk, and also to visit LPL. It was a very wonderful and very beneficial visit for me. This is the first time I visited US, and it was a very different landscape that I'm used to, but it was really nice. So like Ilaria introduced, I am a fourth-year PhD student working with Inga and Evin, my supervisors, and I will show some of the MINDS results concerning the very low mass stars. So this actually volume. I don't know if the Zoom people can hear it, but so I just wanted to start with a. So this was just a video from NASA, which I thought was really nice. So they just show the exoplanets detected in the sky, and you see initially it is radio velocity, and they have sound associated. And as it goes on, you start to see more other observations. So there's transit observations as well. And you see, you can kind of see where you would have your biases and stuff. So once there is a lot of transit stroke, you can also see microlensing happening towards the system. And then at around 2012, I think that's when Kepler and then with K2, I think you can actually see kind of it going along the ecliptic. So we can so yeah, this is just to give a rough overview of like why we are interested in these disks basically. So what we kind of find out is that the most common type of star in the universe or more in the galaxy is the very low mass stars, and the occurrence rates of these terrestrial planets are the highest around these stars. So we expect in the whole universe, or at least in our galaxy, that the most common type of planets would be the terrestrial planets, and it is always interesting to see under what conditions they form and what conditions they evolve. And for that, of course, we study the protoplanetary disks where they form. And here I just show a comparison of how different a disk around a very low mass star is. So when I say a very low mass star, it is something less than 0.3 solar masses. And here is a disk around a regular T Tauri star. And what you can see is in the disk, of course, there are a lot of processes happening. So there is the freeze out of the volatiles causing snow lines. So there is water snow lines, CO snow line. There can be other snow lines of other volatiles as well. And then there is radial transport of processes inwards, but there's also vertical settling of dust. And so there's a multitude of processes happening. And in the T Tauris or sun-like stars, disks around sun-like stars, what you see is the snow line is about 1 AU or few AU. And then the CO snow line is few tens of AU, and the disk in general are like about 100 AU or larger, ballpark. And then the same in the very low mass star. So these are more or less like a scaled down version of a T Tauri star, a disk. So the snow line here would be about a factor smaller, so it would be like 0.1 AU or so. And then the overall disk size in terms of radius, it would be around 10 AU or few tens of AU. And with the midINfrared, what we probe in the T Tauris is around 1 to a few AU, so 1 to 10 AU or so. And in the very low mass stars, it is very small region, so it is less than 0.1 AU. And what that means is,
it seems like the audio is not good.
So for people online, can you hear us well?
It's a little difficult.
Okay, because the microphone is on the ceiling, so maybe you can stand a little bit closer to us, so, and then it will pick up your voice better.
And maybe
can you hear me now?
Project more, speak louder.
Okay. Can you hear me now?
Yes. Yes.
Okay. Needed some calibration. Okay. So the midINfrared emitting region in the very low mass stars is less than 0.1 AU. And as the emitting region gets smaller, you also expect lower fluxes. So it is really hard to observe these very low mass star disks compared to the T Tauris. In terms of signal to noise, you would find a very good signal to noise spectra for the T Tauris, but for the very low mass stars, it is a difficult job to observe that. And if we take a closer look, so the midINfrared region that we probe are generally the surface layer, because there is the optically thick or the small dust grains that are higher up in the disk, and they basically obstruct our view into the disk. So the larger the minimum grain size in these regions, the deeper we can probe into the disk. And yeah, this is just to show that we are probing somewhere between 0.1 to 0.01 AU. And the closer we get, we move to the near infrared. And that is basically what we think we are looking at with the midINfrared. And of course, these were studied with Spitzer, and Ilaria led two main papers for these, looking at a bunch of very low mass star disks. And if you compare them with the disks around sun-like stars, what we find is that the detection rate of C2H2, for example, is higher in the very low mass stars compared to the T Tauris. And HCN was not detected in the sample of 14 very low mass stars, but it is quite common in the T Tauris. And if you look at the normalized spectra, the median of all these sample, what you can see is that there is a quite strong difference between the signatures. So there is very strong HCN compared to the very low mass stars. So what this tells us is there is possibly some chemical composition difference between the two. And also the other interesting thing is that there was no confirmed water detection in the very low mass stars, which is a smoking gun to say that there is possibly a very high C over O ratio in these very low mass stars compared to the T Tauris. But it could not be confirmed like what the C over O would be, but it pointed to a high C over O. And in terms of the dust, what the observations and models together told us is that as we go to lower luminosities or smaller stars, we require higher grain sizes to explain the observations, which basically means that we are probing much deeper into the disk because of the low dust opacities. And this is the MINDS team. This is MIRI midINfrared disk survey. This is the GTO program of EU, and led by Thomas Henning over here, and then also Inga. And this is of course in visual wavelengths, but JWST would look at us something like this. But of course, not all the MINDS team are here. These are just few people. I'm here. But of course, this is spatially resolved. I don't think any disk we have would be spatially resolved like this. But yeah, so we have about 135 hours of observations and mostly dedicated to MIRI, but there are also some near infrared observations with near Campani aspect. We have a total of 51, and out of those, we have a quite diversity, but I'm talking about the 10 very low mass stars of the brown dwarfs. Just to give a context of how the spectra looks, this is the first spectra that we published from the MINDS. So this is a disk around a T Tauri star. This is GWST, and it is a 0.5 solar mass star. And this is generally what you would expect from a spectra. So you have a very strong dust feature and tiny wiggles, which are the molecules there. And you generally find water, CO, CO2, and sometimes C2H2, and also neon lines or hydrogen lines. This is the general expectation from the spectrum. Also, if you look at the PDS-70, which is the other T-Tauri star, which has planets that are actively accreting material in the disk, that is even extreme, you would find a very strong dust feature, and the wiggles are very subtle, but there are molecular emission there as well. So this is the general expectation when you look at a T-Tauri star. So the dust feature is more dominant, and then you would see molecules. So 10 micron region, you would see the emission, and the other regions, it would be basically flat with tiny wiggles. When we looked at the first very low mass star spectra, it was the opposite. So at the 10 micron region, where you actually expect an emission, it was flat. But where you expect a flat emission with tiny wiggles, you actually see broad continuum emission. And this is not the first time this object was observed. This was also observed with Spitzer. And here actually what it says is that it could be that the 10 micron region is actually a silicate absorption, which makes sense. It looks like that. So if you draw a continuum, something like this, and this could be a 10 micron absorption. But turns out that it is not a dust absorption, but instead it is molecular emission on the either side. So usually what you expect in the T-Tauris is an emission something like this of C2H2, for example, or something like this. So this is column densities of 10 to 16 or 10 to the 18 per centimeter square. And this is how you would expect. So there is the Q branch, and then there are the P and R branch on the either side. But what we find is if we just keep on increasing the column density, then they actually form a continuum emission. Similar to how you would expect a dust to form a continuum, it forms a continuum emission in molecules. And this is what is happening in that spectra. So basically the line kind of saturates and it just starts broadening, because it's a Q branch, you have a lot of lines together, so all of them contribute to the opacity and basically build a wall of continuum. And of course, when we fit it, we found that there's just C2H2, but a lot of column density. And then we also find benzene and C4H2, but no water. So there is CO2, but there is no water in this spectrum. And if you compare the column densities with those of T-Tauris, you see that it is water you don't detect. So we just have an upper limit, but the hydrocarbon is higher than whatever we had ever seen in the T-Tauris. And then, yeah, so JWST is very good because it has very high sensitivity and resolution. So at the top is the spectra of ISOCHA 147. So that is one of the very low mass stars. And at the top, you can see the low resolution Spitzer spectra. And there was the C2H2 detection, and the C2H2 is just covered by 3 wavelength winds. But in JWST, you can see how sensitive it is to all these tiny wiggles. And all these tiny wiggles are molecules. So this was a very challenging task to identify what each wiggle is. They're like continuous wiggles from the beginning to the end of the spectra. And if we take a closer look, this is the first object that I studied, my first project of my PhD. So we detect methane and then ethene, and you can already see that these are also forming molecular continuum, and they are all stacked on top of each other in the vertical in the wavelengths. And ethane that was detected for the first time outside the solar system, and then this is acetylene. And HCN, this is not detected in the sources. You can see how low of a flux it is. So you really need JWST to observe it. And here, like this is very complex. You have at least 5 molecules overlapping on each other in the wavelength space. And some of these molecules, we did not even have the molecular data. So we had to calculate them first to actually identify and fit them. So here you can also see that some of them we cannot fit it because we lack the molecular data. So this is only up to around 17 microns. There are still wiggles going on up to 20 microns, but we don't have the molecular data to identify what they are. So in general, this is the richest molecular composition we have seen in a protoplanetary disk. And you can see every single one of the molecule we identify here have carbon in it. So what we find, a conclusion here is that the hydrocarbons are not just abundant, but they are also diverse. And looking at what kind of hydrocarbons we are actually probing or looking at. So here is a study just based on purely energetics, showing what is the minimum energy of the molecular structure and also the fragmentation energy, just to give an idea of whether the molecules are stable. And if the molecule is stable, they just call it magic molecules in these authors. And if you take a look, all the molecules that we find are actually stable, and all of these are magic composition, which basically means that we don't have any radical or unstable molecule that we observe, or at least the ones that we are able to identify. There might be some we are not able to identify. And the column densities, the pressures that we probe tell us that this should be in thermodynamic equilibrium, which is in line with, or that is what you would expect in the inner regions of these very low mass star disks. And again, if you compare the column densities, you can actually see that in this source isochar, the column density is even higher. And if we want to reproduce this whole composition of like hydrocarbons with very little water or no water, we can do it in the gas phase. And if we want it to form in the thermodynamic equilibrium state, then we need a carbon to oxygen ratio much larger than 1. That is the first conclusion. And of course, there are few more sources that we studied. So this is one of the other source, and here you actually see the dust feature. So even in the one that I showed before, there was no dust feature, but here you can see a dust feature, but it is not as strong as in the T Tauris. You can see C2H2 is actually much stronger than the dust feature. And then the puzzling thing was, where is water in all of these spectra? And then Cheng'an actually published this spectra of SZ114, and it is filled with water lines everywhere. So where do we draw the line? When is it water rich and when is it carbon rich? Or basically the question is, whatever we probe in the first 3, are they like one-off? Are they like in a very weird parameter space in the whole population, or is it like common thing? So the next thing that I did was for my project was to look at the entire sample of the mine's very low mass stars. So we have 10 sources, and here what I show is in the green is the detections, the molecules. So y-axis is different sources and x-axis is different molecules or dust or atoms. And at the top there is the detection rate, and at the right there is again basically kind of the detection rate but grouped according to the color. So the reddish color is the organics, the gray is the inorganics, and you can see the highest detection rates are for the organics. So HCN and C2H2 are detected in all the sources, and the most commonly detected oxygen bearing molecule is CO2. And then on the right, what you can see is in the sources where we find more hydrocarbons, we detect less of inorganics. So there is kind of an anti-correlation. There is a lot more that we can study, but I will skip through it for now. And so the thing, like I showed in the spectra, it is really hard to fit each of them spectra because there are so many hydrocarbons and spectrally overlapping. So instead of measuring directly the column densities, what we can use is, if we look at C2H2, there is quite a diversity in the peak strengths of C2H2, and there is also 13CCH2. So we can use the flux ratios of C2H2 and 13CCH2 to use as a proxy for the column density. And if we plot that on the y-axis against the number of hydrocarbons detected or the dust strength, what we find is the more the column of gas we probe, the more the different hydrocarbons we detect, which makes sense. So basically larger column, there are more hydrocarbons that you pick up. And also it anti-correlates with the dust strength, which basically means that the more the dust opacity, the less the column of gas you would probe. So if you have less column of, if you have less dust opacity, then you can probe much deeper in, so a larger column of gas. So which basically tells us the deeper we probe, the more carbon rich these disks are. And although we don't have an estimate of C or O because we don't know where these molecules actually reside, we just plot, say, CO2 to C2H2 peak flux ratios. So here that is the main isotope columns, and here the secondary isotope columns. And you can actually see that there is kind of a trend, and the trend is with the age. So these are the young sources, about 1 to 3 million years, but these are the very old ones. It kind of hints that probably there is an age aspect to it, but it is very unclear still whether it is actually age or if there is any disk structure that is causing it. And not going into too much details, but again, I took a closer look at where the water is. Is it really hard to find water? And then we have 3 detections of raw abrasion bands in these sources, and 3 of these are, and all the 3 of these are actually super carbon rich. So there is water in these carbon disks, and then this is the raw abrasion band, pure rotation lines. So between 16 and 18. So before 16, there's all the hydrocarbons, so you can't see them, and beyond 18, the signal to noise is really bad. So in the top 3 panels, we detect water. And in those 3, we don't have a lot of hydrocarbon emission, but in the remaining ones, I show here that water can be hidden in the spectra. But the thing is, there is so many other wiggles surrounding it, it is really hard to claim a detection. And what we think is happening here is all these wiggles are not noise, but they're just the other hydrocarbons having their P or R branch around them. So in general, water could be hidden in these disks. And if we look at the C2H2 peak to continuum ratio, basically the strength of the C2H2, we find that as we go to smaller stars, the C2H2 becomes much brighter. But for water, not so much. Assuming that, say, whatever we detect here, so assuming whatever we detect here as the actual detection, we can say that water is probably in the same level in all the luminosity range, but C2H2 is very different. So in these sources, where you have a competition between those 2, you would see a very water-rich spectrum because it is spread across the entire wavelength range. But in these, the hydrocarbon P branch is actually spread across an entire range, and water struggles to show up above that level. So what is actually happening in these disks? So we still don't know. We have some ideas. That is what we need to test. And here are 2 very simple ideas, assuming no disk substructures or anything. So there is a smooth disk, and then what Ma et al. Show is that the dynamic transport in these disks are very fast. So what can happen is the solid material, which usually carries oxygen-rich ices from the outer disk, carries into the inner disk, sublimate the oxygen-rich gas into the inner disk, and that oxygen-rich gas can be accreted onto the star. So you preferentially transport oxygen inwards and lose it onto the star. So you'll be left with an oxygen-depleted gas. So you're not changing anything with the carbon, but you're losing the oxygen in the disk. So then again, C or O can be larger than 1. Or the other scenario is you don't deplete oxygen, but you enhance carbon. So what you assume is that in the grains, there is amorphous carbon or macromolecular carbon or some form of carbon basically. And once they cross a temperature range where it can actually sublimate it, it can go back into the gas, and the gas can become super carbon rich. But which of these actually happens? That is the question that we're trying to address. But we still do not have a solid conclusion on it. We have some hints, but yeah, this is And again, there can be substructures that can actually affect everything. Here, this is a very simple assumption that there is a smooth disk. And yes, so I will leave the conclusions. So for sure, because we see all these hydrocarbons, the C or O must be larger than 1, at least according to our models, that is what we see. And the lower the dust opacity, higher the column we probe. And the lower the stellar luminosities, the higher is the hydrocarbon emission. And maybe the disks are not water poor after all. There could be hidden water in them, just hidden by the hydrocarbon emission. And this is a very different environment in which planets would form compared to a T Tauri star. And of course, there are a lot of other papers coming up. Keep an eye out.
So we have plenty of time for questions. Do you want to moderate that, Aditya?
Yeah, so for people online, if you have any questions, you can just raise your hand or just type your questions to the chat and we can pronounce it out. And do we have any questions in the room?
I have a question about you previously showed the flux of like 13C-CH2 and also 13CO2. Yeah, but for that, I remember that for the 13CO2, it is blended with the main isotope log of 12CO2. So how do you get this flux of 13CO2? Is it from the model or?
You mean C2H2 or CO2?
CO2.
CO2 is not blended. So 12 CO2 is at 15 microns, so 14.98 or so.
Yeah.
And 13 CO2 is at 15.4 microns.
But at that part, there is also R branch of.
Oh yeah, yeah. There could be an R branch, but the flux levels are very different. So basically, yeah. So here, what you can see is, so the second peak here, this is CO2, and this is 13 CO2. If there was an R branch, it would be, if this was an R branch, then you expect other vehicles to be at the same level. But this is standing out from the rest of them. So of course, it can have a small contribution from the R branch, but it's not completely R branch. Yeah.
For most of the sources are like that, because I
Yeah.
remember many of them, they don't have very strong 13 CO2 and like it's not significantly higher than the R branch of the.
In most of our sources, we find this, at least when we find more hydrocarbons, we also find very strong 13 CO2, which basically means that you're probing much larger columns. So you saturate your C2H2 or CO2, but you are still optically thin in 13 CO2, so the flux starts increasing.
Okay, thank you.
Ask a follow-up question on this. So does that single peak at 15.5 microns only belongs to the 13 CO2? I mean, there is a peak over there, but
like actually, if you zoom in, I can stop this video at the right. Stop.
That's a nice visualization. Did you make that?
Yes,
Yeah, it's good.
using PowerPoint.
using PowerPoint to do that?
Artisanal.
So yeah, so this is what we claim as 13 CO2. I guess no other hydrocarbon has a feature there that is as strong as this. And if we try to fit this, assuming say 12C to 13C ratio of what you find in the universe, you expect this to be bright enough to be sticking out. So of course there can be other contributions. So here there are other features, but like there can be uncertainty on what exactly the flux level is, but for sure that is 13 CO2.
So I have actually a similar question to this. So you mentioned in your talk that the water could be hidden in the spectrum of many of the observations on many disks. So if that is true, what is the intensity we expect for those water? So if we look at this figure, would that be like the shallow little orange line beneath, or even weaker than that?
Right, let me go to this figure. So if I remember correctly, this panel is the spectra that I just showed now. So you can see that water can be actually the main flux contributor at those levels. But if you go to shorter wavelengths, so here the flux level is about 1 millijansky, but the hydrocarbons are at around 6 to 10 millijansky. So they are like at a ratio of 0.1 to the hydrocarbons. So if you can fit the hydrocarbons and subtract them with the error bars that are smaller than 1 millijansky, then you can actually find out whether there is water. But in most of the cases, as you can see, it is at a level of 1 millijansky. It is really hard to like claim a detection. But we do, in the paper, we do cross correlation tests, and we actually find a positive correlation with water. And we kind of propose that it is possibly water, but it is hard to claim a detection.
Thank you.
So you presented two scenarios at the end to explain the different chemistry in this very low mass stars. Yeah. So, I mean, I know why the first scenario would work, but why the carbon enrichment scenario would be more efficient around very low mass stars, which are, less luminous than TRAPPIST stars.
Yeah, that is one of the arguments that we make in the paper, that probably the main counter argument for this is that if you expect this to happen around a very low mass star, then you should also expect the same to happen around a T-Tauri star. And we don't find such, there are hydrocarbons in the T-Tauris, but such high column densities and diversities we have not seen so far. But the thing is, in the T-Tauris, the dust opacity is much larger. So we are probably not looking much deeper into the disk, while in this you almost see no 10 micron feature. So you basically grow a much larger column density. And probably because it is much deeper into the disk, maybe there is a carbon soup inside, and somehow it is hidden in the T-Tauris. I'm not entirely sure. But it can be a likely scenario.
Do you see any trends between the disk inclination or the dust continuum shape, like flaring of the disk, and the molecule, basically inventory of molecules that you are detecting?
I haven't actually looked into the details of the dust composition and dust strengths. So here you can actually see the normalized dust strengths. So we have only one source that is highly inclined, so close to it, John, and that is the source where this one, which has a weird shape where you actually see part of it in absorption and part of it in emission. But in the rest of the sources, we have no information about what inclination these disks are in. So we have very little information about that. But there is another PhD student who is actually studying what the dust composition is and the grain sizes are. But that is still an ongoing thing. So for a first order of estimate, I just integrate the whole dust feature here as the integrated dust strength. Then just find that there is an anti-correlation with the column density of hydrocarbons.
So Arturo, do you want to ask your question?
Yes, thank you. Thank you for the talk. I have a question about the. Do you have any estimates for this disk? I don't really know about this very low mass disk of the dust to gas ratio.
No, that is really hard question. So
Oh.
the thing is, the dust in these disks are at least so the smaller or the minimum grain size is at least 5 microns is what we think. But we are not sure exactly what the grain size is, and without having a proper information of that, it is really hard to estimate the dust to gas ratio. Like there is one modeling paper by a PhD colleague of mine, which I also put it here. So there is a thermochemical modeling by Jayati Kanwar. So she modeled the J1605 spectra with a full Prodemo model, and she finds really low dust to gas ratio. Like
yeah, because
yeah.
Thank you. Yeah, it's yeah. My question is related to, like, could it be that these are carbon rich now because at some point they were oxygen rich when the ice sublimated, but now it has. Once all your dust goes away, that source of ices may disappear. So you are left with a carbon-rich disk eventually.
Yeah, so that is what the first scenario predicts. And the first scenario also predicts that because you lose all the pebbles, your millimeter flux should also be very low. And most of our sources are a non-detection in ALMA, but some of them have really strong dust millimeter observation. So there is still a diversity. So maybe there is something to do also with the gaps that, say, rocky planets can form in these tiny disks. So it is not a clear picture yet, but like out of these two scenarios, the first one seems more promising if you just look at a bigger picture.
Okay, very interesting. Thanks.
Serena, do you want to ask your question?
Yeah, actually, I was having similar question, and I'm curious if at some point, for instance, the oxygen depleted area, actually the oxygen was more dominated, for instance, at the very beginning. Later, it became like a carbon more enriched at very close part of the disk. So my question was sort of related, but then when you say that there's a very inner disk that is carbon enriched, how inner disk that should be, and would it be possible that only as a carbon enriched area get developed much later for certain processes? And I wonder what could cause that problem. I mean, the carbon enrichment.
So the region that we are probing here is less than 0.1 AU. So that is like the very inner regions.
Yeah, so suppose, I wonder if there was also oxygen was more dominated, at some point the carbon gets enriched.
Yeah, I think that is what is proposed in Chengyan's paper, where they actually see that the spectra is really water rich. And this is part of Loopy, and I think it is 1 to 3 million year old. And what we have are a sample, but in that we have really old ones that are really carbon rich. Now the ones here you can see the cyan one and the blue one at the bottom right are upper SCO and PWA, which are at least older than 5 million years, and they seem to have more hydrocarbon emission than the rest of them. So it could be that what was proposed in Chengyan's paper. So like they are going through a phase where you initially bring in the oxygen material from the outer disk and you sublimate, and there is an oxygen-rich phase, but then you lose it pretty quickly, and then you turn to a carbon-rich phase. That could be, that very well could be a scenario.
Yeah, thank you.
Are there any other questions from online audience or?
Maybe you can comment more about the implications for planets that will form in this disk. Because, I mean, you did that in the paper, so I think it's interesting for.
So if we just assume these are the possible two scenarios, then if the planets are forming in such a scenario after, like at the current stage when we are observing, then the gas versus the dust that that they would used or they would need to form the planet would be very different. So if it was an oxygen depleted scenario, the dust is not too much of a difference. So it would more or less be like the dust in the T-Tauri's, and you would have, say, Earth-like silicate composition for the planets, but the oxygen would be depleted. So your primary atmosphere that would accrete would be super carbon rich. But in the other one, if it is actually carbon depleted dust, and I don't know to what extent the carbon depletion, like where exactly this depletion soot line is, where exactly the plant forms. But if it forms in the region where the carbon depletion happens, then maybe the dust is super carbon depleted. Maybe it is something, okay, then it would be more similar to Earth, which is more carbon depleted, is what I think. But again, it would still have a super carbon rich environment. But if it formed much before this, say in a water and rich environment, it would be then probably would be very similar to the T-Tauri's. So I think it is more of when it forms and which condition is more the reality. But that will surely have strong implications on the planet composition.
So what do you think for these two scenarios would be like, could help us to finally distinguish which one is more likely to be the true?
I think more observations and also detailed fitting of like each of these spectra. So so far what we have tried to do with these spectra are 0D slab models, and 0D slab models only give us a rough estimate of number of molecules that there are in this that are emitting. But what we need is a gradient. So fitting it with 1D temperature and column density profiles and putting them against the radius, that would give you a good estimate of where these molecules live in the disk. And combining that with water detections, then you can actually say what exactly the C or O is and where these are. And then I think we can isolate which one is true. And of course, we will need ALMA observations as well, because the first one has a very strong implication on the ALMA millimeter fluxes. So ALMA observations will definitely help a lot.
Any other questions? Last call for questions. Okay, if there's no.
Yeah,
Thank
that was a good time.